So yesterday we had intended to get there, but we ran out of time, so today we will get there. So we'll start there. We're going to talk about improper integrals. And hopefully we have time to talk about both types. There's type 1 and type 2. Kind of like diabetes. But this will be less hazardous to your health. All right. So type 1 is motivated by what we've been doing with series. Right? Namely, you have a series, and you want to know whether or not it converges. Okay, so you add up an infinite number of things. Does it? Right? Does the limit of the partial sums converge to something? Right? That was our question. And a related question is suggested by the following picture. Let's say I take this graph, and let me see. Let me pick some point. Call it what? I don't even need to give it a number. Let's call it some A. And I start looking at the area under this curve. Okay, and let me go to here. Okay, so that will be my B. Okay, so this is my function f of x. And we already know how to find the area of the region bounded by the curve, the x-axis, and between x equals a and x equals b. Right? And of course, how do we do so? Take the integral, right? From a to b, f of x dx. Somebody took your seat. We replaced you with Tom. Okay, so I can compute this area. Right, now remember when we talked about the fundamental theorem of calculus, FTOC, we had this special function that we called g of t. Let me, just for fun, let me replace this b here with t, just so it looks like what we did in the old days. Remember we defined this g of t actually as the area under the curve between a and t. And it was kind of this transparency function, right? You could move t out, and then this g of t would get bigger, right? You'd get more area under it. Okay, we had funny rules like g of a, right? That's when you just had the straight line, and that was just 0, right? There's no area on just a straight line. Okay. Okay, so let's take this t and start pushing it out. Pushing it out. You get more and more area. The question is, does that area, if you kind of view it as it's not really a sequence, but let's think about it as a sequence, right? You keep moving that area out and out and out. What's happening to this function g of t? Well, you're getting more area. It is increasing. But is it increasing by too much that it will just blow up to infinity? Or does it somehow converge to a value? Okay. So the question that I'm asking is, what is the limit as t goes to infinity of g of t? Okay. So this is going on forever. So your inclination is that, well, you can't possibly, it has to be infinity. All right, but we've already seen that you can add up an infinite number of things and get something that converges to a finite number, like a half plus a fourth plus an eighth plus a 16th, right? That converged to 1. Okay. So if you take this t and let it go to infinity, it could be that this g of t actually converges to a finite number. Okay, so let's see an example of it. Let's say we let f of x equal 1 over x squared. And we'll let a equal 1. Okay, the a being this a over here. So I want to know what is the limit as t goes to infinity of g of t. Right? G of t is our transparency function. It's the one that just gets more area as you make t bigger. Okay, well, we can write down what g of t is. It's the integral from a to t of our function 1 over x squared times dx. Okay, well, if you forget about this limit for a second, this is just a nice definite integral. We can compute this, right? Okay, so we'll just leave the limit on the outside. Now let's see, what's the antiderivative for 1 over x squared? Negative 1 over x, right? It's x to the minus 2. Okay, you have to add 1 to the exponent. That gives you a minus 1, 1 over minus 1, and then x to the minus 1. So yeah, minus x to the minus 1 or minus 1 over x. So minus 1 over x. And then you have to evaluate it at a. Well, we know what a is actually, right? We know it was 1 and t. Okay, so we're applying the fundamental theorem here. And let's see here. Okay, so when you evaluate at t, you get minus 1 over t minus, now you evaluate at 1, so you get minus 1 over 1. So minus 1 over 1. Okay, so this is just plus 1. And then you have minus 1 over t. So the limit as t goes to infinity of minus 1 over t plus 1. Okay, so what happens as t goes to infinity to this expression? What does it become? Yeah, well, as t goes to infinity, 1 over t goes to 0. Minus 1 over t still goes to 0. Plus 1 goes to 1. So this just is 1. So this is maybe a little bit surprising. As you add more and more of the area, and this roughly is what 1 over x squared looks like. As you add more and more of the area, right, the function that describes how much area you have actually converges to 1. So this gives us justification for saying the area under this curve between 1 and infinity, right, is 1. So with this in mind, we define the integral from a to infinity, okay, for any a, f of x dx to be, well, it's the limit as t goes to infinity of g of t, which is just the integral from a to t of f of x dx. Okay, so that's our definition. Okay. Now, as before, oh, Dina, yeah. Okay, fair question. Well, in the finite case, right, if we're just looking at finite limits, we certainly know what to do already. Right? We know the answer. The interesting question then is, I mean, calculus, of course, is always dealing with infinity, infinitesimally small, infinitely big, right? These things naturally come into it, right? When we defined the definite integral, for instance, right, we drew these rectangles, and we made them infinitely small, and we made infinitely many of them. Right? So calculus becomes a natural place to talk about the infinite. Right? We have the tools to do so. Right? We didn't have the tools before. For instance, limits are ideal for talking about infinity. Before you have the notion of a limit, it's very difficult to talk about infinity. So here we're interested because, well, we start with our our infinite series, okay? And we're interested in questions about those. Okay? We start to ask now about integrals, right, of possibly infinite areas, or at least over infinite intervals. Because later on we want to get back to series and use this theory. That's a partial answer. I don't want to go too far astray at this point. Okay. There's some hypotheses that we always want when we integrate. Right? For instance, when I wrote this down, okay, so here capital F is an antiderivative, right? Okay, when I write this formula down, right, this means f of b minus f of a. All right, this is, of course, f-talk2. This is our second version of the fundamental theorem of calculus. Okay? This is not always true. Right? I need at least one good assumption on the function. Right? You remember the assumption? In fact, this problem showed up on the midterm. Right? What do I have to know about this function for this to be true? Almost. I don't need it to be differentiable. Continuous. Right? Need it to be continuous, right? So this is when f is continuous on the interval AB. Now, I should say you actually don't need continuity. You can do with something a little bit less. But this would require a very long discussion, and usually we wait for, well, maybe even grad school to start talking about it. So, but continuity is for us, that's the condition we want. Okay? So we're going to need a similar condition here. Okay? So right, we define the integral from a to infinity f of x dx. When f is continuous on the interval a to infinity. It should be continuous everywhere there. We don't want to allow weird jumps or even things that might go to infinity. Not yet, anyway. Let's see. Okay, now, there is nothing special about going from a to infinity. We could go the other direction. Right? We could go from b, say, down to minus infinity. Right? And everything's going to be the same. We just have to we just have to switch everything up. Instead of t going to infinity, t will go to minus infinity. So, like that. Okay, so again, when f is continuous on, now we'll go minus infinity to b, we define the integral from minus infinity to b, f of x dx, to equal the limit. Well, now it's really the same function, only we want to reveal this way. So instead of t going to infinity, we want t to go to minus infinity. Okay. It's the same idea, though. It's just going on the other side. Okay. Now, there's a way to combine both of these, which is, so if, let's say, f is continuous on the entire real line. Okay? So the domain is all real numbers, right? And it's continuous at all real numbers. Then, well, for any real number a, we can define the integral from minus infinity to infinity of f of x dx. And the way we do it is just by breaking it up into two different integrals, right? One that looks like this, and one that looks like this. And we just break it up at, say, a. So this becomes the integral from minus infinity to a plus the integral from a to infinity. Right? And so then you can evaluate these separately. Usually I make a 0 because 0 is usually easier to calculate with, but you can break it up anywhere you want to. Okay, let's do an example. And we'll talk about a problem. Let's integrate from minus infinity to infinity the function dx over 1 plus x squared. Okay, first, we need that the function 1 over 1 plus x squared is continuous on all the real numbers. So first thing is, it's a rational function, so if it's defined, it is continuous. But is it defined everywhere? Do we have any problems? Well, it's a fraction, so if you had a 0 in the denominator, that would be a problem. But can you make x squared plus 1 be 0? No, right? It's always positive. Okay, so we're defined everywhere. So we can split this up into two different integrals, right? That's what this guy over here says. Okay, and where do we split it up? Well, we can split up anywhere we want to. Where would you like to split it up? 0, what a good idea. Okay, so let's split this up. Okay, so we'll go from minus infinity to 0. And then we'll go from 0 to infinity. Okay, so now we need to evaluate each of these. So for the first one, let's do them separately. Minus infinity to 0. This equals, well, by definition, this is the limit as t goes to minus infinity of the integral from t to 0 dx over 1 plus x squared. Agreed? Okay. Okay. So let's see here. We need an antiderivative for 1 over 1 plus x squared. Chris knows this one. Tong is impressed that I can. It's a little magic trick I have. Dude. Pardon? You mean in this definition? No, no. Here we've actually chosen a real number. Is infinity a real number? No. Infinity is not a number. Here, this is just a symbol that we use. Right? We can't actually write this. That's the whole thing, right? When we say this, we have to give this a real meaning. Okay? And the real meaning is that we evaluate these integrals, and then we look at the limit as t goes to infinity. Okay? And what does it mean that t goes to infinity? It means t gets arbitrarily large. Right? T never gets there because there's no there to get to. Infinity isn't an actual number. Okay? The best we can do is say, well, it's something that's bigger than any real number. But that's about all we can say. Okay? But even calling it something is already problematic. Something doesn't work. Okay, so Chris tells us the antiderivative is going to be arctan. So we're going to get the limit as t goes to infinity, minus infinity, of arctan of x evaluated at t and 0. Okay, so we get the limit as t goes to minus infinity of arctan of 0 minus arctan of t. Okay, so now we need to know what is arctan of 0. So let's see, we need to find an angle whose tangent would be 0. Let's see, tangent is sine over cosine. That'll be 0 if, well, let's see, it's a fraction. The fraction is 0 when the numerator is 0, so when sine is 0. When is sine 0? At 0, right? Okay, so at 0, we're going to get it. So this is just 0 here. Okay. So then we just get minus arctan of t. Okay, and now t is supposed to be going to minus infinity. Okay, so for what angle would we be going to minus infinity? Oh, you're thinking, okay, when you're over here on the 180, so, or at pi. So the arctan function, remember we have to restrict the domain and the range. That is, we restrict the range so that it's not a multi-valued function, right? What we're really doing is we're restricting the domain of tangent, right? So that this is only an inverse for tangent between minus pi over 2 and pi over 2. Right? We just look at it on this half circle. So the only place where it's going to be 0 is here. We skip that otherwise. Otherwise, you'd have multiple options. And we don't want this function to have two different outputs, 0 and pi. This is a good question. Okay, so this is 0. Now, where is for what angle would our tangent end up being, start approaching minus infinity? So let's see here. So again, tangent was sine over cosine. And those fractions go to infinity if the if the denominator goes to 0. So we need a place where the cosine is 0. Okay, so pi over 2 does it. Okay, what's another place that would do it? 3 pi over 2, right, or minus pi over 2. Now, we want it to be going to minus infinity. Now, cosine is going to 0, and the sine, well, up here the sine is positive, right? And the cosine is also positive. So that wouldn't be going to minus infinity, that would be going to positive infinity. So down here, well, now the sine is negative, and the cosine is still positive, so this would be going to minus infinity. So that's the angle we want, is minus pi over 2. So as t goes to minus infinity, arctan of t goes to minus pi over 2. And so we get 0 minus pi over 2, which is pi over 2. Okay, that takes a little bit of, there's an argument building into here, right? You have to understand this. You have to think about it a little bit. This is not the trivial part, even though I wrote nothing. Okay. Now what if we do it the other way? We go 0 to infinity. Well, by definition, this is the limit as t now goes to infinity, integral from 0 to t dx over 1 plus x squared. Okay, and everything is going the same, right? It's the same function, so when we integrate, it's all good. Limit t goes to infinity, arctan, right? Well, it's going to be arctan of x, and we evaluated at t and 0, only in the opposite order now, right? And we already know the arctan of 0 is 0, so we just get arctan of t. And we've actually already solved this problem, right? As t goes to infinity, what does arctan of t go to? Pi over 2, right? It's the one up here, right, where it's positive. This is, again, pi over 2. Okay, so this tells us this integral is pi over 2, and this is pi over 2. So the area under this curve, under the entire curve, is pi. Okay, so this curve is looking roughly like shouldn't go. So if you add up all the area under this thing, it ends up being pi. Incidentally, you notice we got the same thing on the left side as we did on the right side. Why is that? It's symmetric, right? Why is it symmetric? Because it's an even function, right? 1 is an even function. X squared is an even function. So their sum is an even function. So 1 over it is an even function. So actually, right, if you put in the negative values, it's the same as the positive values. So you actually had to compute one of these and then just multiply by 2. Okay, very good. Questions? Yeah. We can't use 3 pi over 2. And the reason why is that, so when you define the arctan function, you're using as your tangent function, right? This is supposed to be the inverse, right? You're using as your tangent function the function that goes from the real numbers to, got it backwards. The function which is going from minus pi over 2 to pi over 2 to the real numbers. This is, you're restricting the domain of the tangent function. When you make all these arc trig functions, you always are doing this. You're restricting the domain. And that way, that the arc tangent function, goes from the real numbers to minus pi over 2, pi over 2. So this is the choice we make. Now, that's what I say about it. So so this is the choice that we make. Okay. That way we don't have duplicate values. We don't want the arctangent of one real number to have 2 different values, because then it wouldn't be a function. Okay. All right, so now let me point out a potential difficulty. Something that is bad. Well, we defined these. So by the way, these are what we call improper integrals. Right? The improper is just saying there's something infinite going on. We defined it in terms of a limit. And what do we know about limits? What don't we know? Well, sometimes limits exist, but sometimes they don't exist. Right? If they don't exist, then this doesn't have any. Say this limit doesn't exist, then this has no meaning other than it's just a limit that doesn't exist, which means this improper integral doesn't exist. Right? So let me give you an example where this happens. And what's surprising about this example is that it looks very similar to the first example we did. So let's and copy over what we had before even. F of x equal 1 over x, but I'm not going to put a square. I'm just going to put an x now. Okay? Basically the same problem, right? 1 over x instead of 1 over x squared. Okay, and we'll still let a equal 1. So I'll be interested in the integral from 1 to infinity of 1 over x dx. It's the same problem. What could go wrong? Okay, so this is the limit as t goes to infinity, 1 to t dx over x. Right. Okay, now what's an antiderivative for 1 over x? ln of absolute value of x. Do we have to worry about the absolute value here? No, because all of our inputs are going to be positive numbers. So this is ln of x. Oops, forgot the limit. Limit as t goes to infinity of ln of x evaluated at 1 and t, which is equal to the limit as t goes to infinity of ln of t minus ln of 1. What's ln of 1? 0, right? Because e to the 0 is 1. So there's actually nothing to subtract. Okay. So what's the limit as t goes to infinity of ln of t? Infinity, right? ln of t, it shoots up. Right? It doesn't go. It starts going very slowly up, but it goes up. It goes to infinity. So this limit doesn't exist. Right? It's just an infinite limit. Okay, which means that this integral doesn't exist. Which means you can't write down what the area of it is. You just know well, there's infinite area under that curve. Okay. Now this is very strange because if you graph 1 over x and 1 over x squared, they look awfully similar. And we'll start it at 1, say. But somehow 1 over x squared sinks down fast enough, and 1 over x doesn't. This just collects too much area along the way. It's kind of strange. Okay, so this just you have to always say with these things that you have this equality if this limit exists. I mean, you define it as if it's a number if it exists. If this limit doesn't exist, then this thing doesn't exist. Right? Same thing happens over here with the negative one, right? This limit just might not exist, and then this integral doesn't exist. And what if you have a minus infinity to infinity? Well, then of course you always have to break it up into two of them. Right? And this one might exist, and this one might not. So what do you do then? Right? Well, something which exists is fine, but something which is not, you can't add to it. Right? Okay, now here's the really nasty thing. What if I do the integral from minus infinity to infinity of 1 over x? Yeah, Dina? Yeah? If it was an even function, and one of them was defined, then the other one has to be defined, right? Because it has to be exactly the same area under it. So if one is defined, then the other one will be. But if one is defined and the other is not, then you can't mix the two. But here's a related question, which is where we have an odd function, 1 over x. Okay? We're going to integrate from minus infinity to infinity. Right? Now, there's actually another problem which I'm not mentioning here, which is, what do we integrate? If we go from minus infinity to infinity, how would I want to split this up? Well, I always want to split it up where? 0. Does 0 have a problem at 0? Yeah, okay. So this is already quite bad. It doesn't even satisfy the basic definition, right? Okay, but, okay, so we can't do it like this. Okay, so let's instead go from 1 to infinity, and then go from minus infinity to minus 1. Now, what does the graph of 1 over x look like when you go into the negatives? Well, remember, it just does the opposite. It does the same thing, but it reflects across the origin. Okay, so you'd be getting, well, if there's your 1, you'd be getting all this area. Okay. Now, it's the exact same area, but it gets a negative sign in front of it. So what should it be? If I add up these two, should it be 0? Because that's all positive and that's all negative and they cancel each other out, right? Or undefined. And we decide on undefined instead of 0 for the exact same reasons we have this whole 1 minus 1 plus 1 minus 1 plus 1 minus 1 business. So you can get into some nasty things with it. Yeah. This is, I didn't break this up. These are not equal, what I just did. I'm just saying write down these two separate integrals. Okay? We know that this one does not exist. This limit doesn't exist. And for the exact same reasons, this one won't exist. But we also know that the area under this curve is exactly the same as this one. Right? If instead of having infinities, I put a t here, right? T and minus t, it'd be exactly the same, except they'd have negatives. This one would have a negative because it's all below the x-axis. Right? And what I'm saying is you might think I should define this to be 0. But in actuality, we say this does not exist. That's the way we talk about these things. Because otherwise we get into these 1 minus 1 plus 1 minus 1 problems. Okay. So here's an interesting question. We saw that if you did dx over x from 1 to infinity, that will not converge. That will diverge. And if you did dx over x squared from 1 to infinity, that it will converge. So we'd like to write down something. If you have just dx over x to the p, we want to know whether it's going to converge. Okay, so that's what we'll do next. Dina. Nope. It means that we don't, it doesn't mean infinity, right? In this case, we can always write, when it's not a number, we can always write it does not exist. We can always write that. Infinity is a little more specific way of saying it doesn't exist. Okay? Here, we know that the integral doesn't exist, but we know that the reason why it doesn't exist is because it gets infinitely large. Okay? Over here, we can't even say that. All right? We just, this is getting infinitely big, this is getting infinitely small. How do you add those things together? We don't know. So we just say does not exist. We could write does not exist over here too. It just wouldn't be as much information. Oh, I mean, look, this one here, this bit goes to infinity, right? Well, just the negative of it. This one goes to minus infinity. How is what infinity? Well, you don't have a value. Infinity is not a value. It's not a number. All right? It doesn't make any sense to write infinity plus negative infinity. Right? This doesn't make any sense because they're not numbers. No. Right? For instance, if you took the limit as x went to infinity of x minus the square root of x, right? Or if you write plus minus the square root of x, right? These are both going to infinity. Right? But you might, but this one's going faster. So should it be 0? But I mean, this one is really going faster. At any step along the way, the difference between these two is growing. Right? So couldn't I make an argument that it's 0? Or infinity, rather? Right? So you start to have these little questions pop up. And well, in differential calculus, we saw ways last term of handling situations like this and figuring out what the limit actually is. Right? But I can give you functions that look like infinity plus minus infinity, where it'll converge to 0, it'll converge to minus infinity, it'll converge to plus infinity, or even to a real number. Right? So plus is only defined for real numbers, and infinity and minus infinity are not real numbers. Of course, this is the interesting thing about limits, is you try to deal with these situations. Okay. It's not. you can only add these together if they both converge to real numbers. Right? This converges to infinity. This goes to minus infinity, so you can't add them together. Because you don't, I mean, what would it be? Infinity plus minus infinity. There's a lot of different answers to that question. It doesn't make any sense. I mean, because we have not defined plus in regards to infinities. It only is defined for real numbers. Up until, well, yeah, but when do you get to infinity? So here's another question, right? If I do it, let's say I do the first, let's say instead I go to infinity, I just go to 1 million. Okay, and then over here I go to minus 1 million. Okay? These will give me the exact same values, except this one will have a negative in front. And so when I add them up, I'll get 0. And if I do it, right, if I always keep it at the same t here as I have here, they'll always cancel out. Right? But why isn't it the same as infinity? Well, what if instead of going t and t here, I go t plus 1 here and t here? No, these are two separate integrals. I can let t go to infinity at any rate I want to. If I put a t plus 1 here and a t here, now this one is bigger and this one is smaller. And so when I add them up, I actually get something positive. If I put a t plus 1 here and a t here, now this one would be a bigger negative, and this one would be a smaller positive, so I'd get something negative. Oh yeah, I mean this definition. No, when you're computing these things separately. I mean, I'm using the letter t in both places, but when I say t is going to infinity, there's no fixed value of t that you're using. All right? And you can I could call a different letter, and then probably even there's just no way to compare them. All right? It's really the same problem we had as when we tried to compute this. Right? It looks like 0, 0, 0. And that's what we'd be doing if we did this the same t at each point. Right? But I could first compute the 1, and then go minus 1 plus 1 is 0, minus 1 plus 1 is 0, minus 1 plus 1 is 0. So I have 1 plus 0, which is 1. Right? Or I could do the minuses first and get a minus number. It's not a number. It's treated as you use it. You don't even use a value. You don't want to specify it as anything. You just want to say, when I say infinity, I'm saying bigger than any real number. That's right. Well, I'm not saying that there is a number that is bigger than every real number. I'm saying something which is, for any real number, this is bigger than it. Okay. When I say it goes on forever, that means it doesn't stop, which means for any real number, this goes past it. Right? But it never has to get to the horizon. This is actually a very good discussion, and I hate to quelch it at all, because these are really important concepts in mathematics, and these ideas are what people struggled with for a long, long time. Cantor, when he started talking about infinities, he got a lot of trouble for these things. And the people who worked on the foundations of calculus, right? The reason why they made all these definitions of limits with all these epsilons and deltas, it was because they were so bloody confused by these infinities. And so they had to give these very precise definitions to deal with them. Because otherwise you got into trouble. You start using infinity the way you intuitively want to, things like this, right? And you get into trouble. Oh dear. Okay. So we've run out of time for today, but this is okay. So tomorrow we're going to, I'll show you the p-test, which is not about steroids, and then we will look at type 2 improper integrals, where we handle what happens if you have a discontinuity in your domain.